Professor John Polkinghorne, who is a pioneer of the modern discussion of science and religion. He's written numerous books, many of which are on our bookstall, so do browse and buy. John started life as in mathematical physics. He was professor of mathematical physics here. He's a fellow of the Royal Society. And then he retired early from that in order to train for ordination in the Church of England. He worked in parishes for a while, then came back to Cambridge, was Dean of Trinity Hall and President of Queen's College. He's gone on writing, still very prolific, and he is, of course, a winner of the Templeton Prize, and he's also been knighted by the Queen for his services to science and religion and his participation in national committees and so on. So it's a great privilege to have you talk to us, John.
Thank you, Ronnie. It's a great pleasure to be here. Well, as you just heard, I'm both a physicist and a Christian. More specifically, I'm a particle theorist and an Anglican priest. And when people hear that, they sometimes give you a funny sort of look, sort of mixture of incredulity and suspicion. As if you said, I'm a vegetarian butcher. Because they think that science and religion are at war with each other, and you really ought to decide which battle line you're going to join. Well, of course, I don't think that. I believe that science and religion are friends and not foes, and the basic reason I believe that is that central to both is the search for truth. The search for truth to be attained through well-motivated belief. The question of truth, of course, is as essential to religion as it is to science. Religion can do all sorts of things for you. It can guide you in life, it can strengthen you in the approach of death, but it can't really do those things unless it's actually true. Otherwise it's just a wishful thinking illusion. But the question of truth is of great importance. But of course, science and religion are looking at different aspects of the truth. We live in a reality of very rich complexity. They're looking at different dimensions of that complexity, and they are asking different questions about it. Science, I think, has achieved its very great success, in some ways by the modesty of its ambition. It doesn't seek to ask and answer every question you might ask about the world. It asks the question of how things are happening. What is the process of the world? And of course, it has been stunningly successful in finding answers to that question. And we should take those answers with gratitude and with seriousness. But there are many other questions to ask about what's going on, which are meaningful and necessary, which aren't just covered by looking at how things happen, but more concerned, if you like, with why things are happening. Is there meaning and purpose and value in what is going on? These are the sort of questions, it seems to me, that a religionist perspective on reality sets out to address and to answer. So I think I need both the insights of science and religion in that sense, and because we're perfectly familiar that you can ask, and indeed you need to ask, to fully understand it, the same, both questions, how and why, if you like, about the same event that's happening. If I take a homely example, which I've used many times, you come into my kitchen at home, and the kettle is boiling. I put on my scientific hat, and I say to you, the kettle is boiling because the burning gas heats the water. When the water reaches to 100 degrees Celsius, a phase change takes place. The liquid turns into gas, or in plainer words, the water boils. Of course, that's true, and it's worth knowing. But nothing stops me taking off my hat, my scientific hat, and saying to you, the kettle is boiling because I want to make a cup of tea. Would you like to have one? I don't have to choose between those two answers. The answer of process and the answer of purpose. They are both meaningful. Indeed, to understand the mysterious event of the boiling kettle, I need to ask and answer both those questions. That's why I see science and religion as not being enemies of each other, but being friends of each other, not being in conflict with each other, but being complementary to each other. Another difference between the two is they look at a different dimension of this rich complexity of reality. Science essentially looks at the world at the level of objectivity. It treats reality as an it. It's something that you can kick around, pull apart, find out what it's made of. Sometimes on a very grand scale, as has been happening at the LHC. in recent months. And that gives science its great secret weapon, really, which is the weapon of experiment. I was a theoretical physicist, a pencil and paper sort of chap, but I would gladly acknowledge that during my 25 years or so in the subject, its discoveries were largely driven by the discoveries of our experimental colleagues. The theorists were always struggling to make sense of the latest message coming from the experimentalists. And of course, that means that it is easier, much easier, for science to establish intersubjective agreement about things, because there is this sort of neutral, objective realm, reality as an it, if you like, which science is investigating. In principle, if you don't believe what I tell you about what's going on, you could do it for yourself. You won't be able to build a machine to make the Higgs boson in the back garden, but I mean, there has to be a certain amount of give and take about these things. But there is this degree of objectivity. But we all know, of course, that there is a great swathe of human experience, indeed a swathe of the greatest significance and importance, in which we encounter reality, not as an it, as an object, but if you like, as a thou. We encounter reality as a person. And we all know that when we enter that realm of personal encounter, testing has to give way to something much more like trusting. I'm always setting little traps. See if you're my friend, but I shall soon destroy the possibility of friendship between us, because it can only be based on mutual respect and mutual trust. So, science and religion are not doing the same thing. They're not rival, they're complementing each other. And I want to take both seriously. And that means, of course, there are going to be some points of contact between them, at which they were able to say things to each other, which the other side has to listen to and enlarge its perspective on reality by taking that into account. And also there will be gifts, therefore, that one side will be able to give to the other. One obvious point of contact is when science and religion are looking at the same sort of phenomenon, but interpreting it from their different perspectives. And I suppose the most striking and obvious example of that is the history of the universe itself. You know, we live in a universe that has a remarkable history. As you all know, it started 13.7 billion years ago. It started extremely simple. It's an almost uniform expanding ball of energy, which is about the simplest physical system you can think about, actually. One of the reasons why cosmologists talk with a great deal of justified confidence, I think, about the very early universe is just a very easy thing to think about. So science sees that extraordinary story that the world, which was a ball of energy, is now the home of saints and scientists. An extraordinary story of emerging complexity and richness can tell us that story and many of the processes by which it's happened. But then there's the question of, is there something going on and what's really happening in cosmic history? Is it more than just one thing after another? Now, I won't say any more about cosmology, because of course Paul Shannard is going to, who's just coming actually, is going to talk about that after coffee, and I very much look forward to hearing what he has to say. I've just made one observation before I leave that particular topic, and that is to remind you that the doctrine of creation, theologically understood, the doctrine of creation is not about how things began, or not solely about how things began. It's not the answer to the question, who lit the blue touch paper of the Big Bang. It's an answer to a much deeper question, Leibniz's great question: why is there something rather than nothing? God is as much the creator of the world today as God was 13.7 billion years ago, because the role of the creator is to hold the world in being. I believe that the world would not be there, we would not be there, unless God held us in being. Of course, we can't perform the ultimate experiment, remove God and see if the world disappears, but I believe that is the case. I think it's a point. And when scientists talk about these things, they're pretty unsophisticated philosophically or theologically, and I think that's true of my former colleague, Steve Hawking. When Steve produced his very interesting speculative theory that the universe is perhaps just a sort of smooth, four-dimensional space-time egg, which may or may not be true. I mean, it's a speculative theory, and there is no point of beginning for the headache, no, sharp point on the ache. He was naive enough to say, what place then for a creator? The answer is every place. That's the ordainer and sustainer of that space-time ache, if that's what the universe is. In fact, right at the end of the book, as you probably remember, Steve talking about beautiful equations of theoretical physics, says what breathes fire into the equation and gives them a universe to describe. That's the question. Why is there something rather than nothing? And that is the question. That is the aspect of creation, which the doctrine of creation is addressing. But I leave the rest, all the details, which are very interesting and fascinating and important, I leave to Paul after coffee. Another connection between science and religion, which is I think of very great importance and significance, is that though of course they don't answer each other's questions, we have every reason to believe, for example, that scientifically statable questions will receive scientifically statable answers. It's a bad mistake, I think, to go for the God of the gaps, as people say, to say science can't explain this today, tomorrow, or tomorrow, therefore we'll have to invoke God to poke a finger and bring that about. That's a mistake that is being made, I'm afraid, not only by the flat-footed literal creationists, but also by the intelligent design. I think we have every reason to believe that if scientifically statable questions receive scientifically statable answers, even if the answers are in fact really difficult to find. I mean, we still don't know the biochemical processes by which life, replicating molecules and so on, began here on Earth. I hope one day we will. And I certainly don't think that we have to rule out a scientific explanation. So that's, but there are questions which, as I've already suggested, which go beyond the questions that science addresses. And interestingly, some of those questions arise out of our experience of doing science, but are not themselves scientific in character, and therefore cannot be answered by science, though they are meaningful and necessary questions. If you like learned language, you can call these questions meta-questions. They take you beyond their starting point. And I just want to, Paul, when he talks about the anthropic principle, we'll have to talk about none of these meta-questions after coffee, but I just want to address one meta-question. What I want to say to you now, it's a very simple question. In fact, it's so simple that most of the time we don't even stop to think about it. And it's this: why is science possible at all in the deep way which it has proved to be? Well, you might say that's pretty obvious. Evolution necessity means we have to understand the world to survive in the world. It must have shaped our brains so we're able to make sense of what's going on around us. And of course that's true. It's true up to a point. But our ability to understand the world, to penetrate deep into the secrets of the world in which we live, seems to me vastly to extend beyond anything that is required for survival necessity, or anything that could plausibly be considered to be a happy spill-off from that survival necessity. I mean, it's one thing to be able to figure out that it's a bad idea to step off the top of a high cliff. Not quite such a danger in this part of the world as in some parts of the world, but it's something that's worth knowing. It's something quite different when somebody like Isaac Newton came along. An astonishing creative leap of the human imagination is able to see that the same force that makes the high cliff dangerous is also the force that holds the moon in its orbit around the Earth in its orbit around the Sun, to discover the mathematically beautiful law of universal inverse square law of gravity, and in terms of that, be able to explain the behavior of the whole of the solar system. That takes us far beyond anything we need for everyday survival. I'm rather fond of the Sherlock Holmes stories, and you may remember that when Holmes and Watson first meet, it's in the study in Scarlet, when they first meet, Holmes is pulling Watson's leg from the start, and he pretends not to know. And he says to Watson, I don't know, he says, I don't know, does the Earth go around the Sun, or does the Sun go around the Earth? And the good doctor is shocked at his apparent ignorance on the part of the great detective. And Holmes says to him, what does it matter for my daily work as a detective? Of course it doesn't matter at all. But we know many things we don't need for our everyday lives, our everyday survival. The world has proved to be astonishingly rationally transparent to us. I worked in quantum physics, and the quantum world is quite different from the world of every day. It's cloudy and fitful in its character, compared with the clear and orderly world of every day. In the quantum world, if you know where something is, you don't know how it's moving. You know how it's moving, you don't know where it is. That's Heisenberg's uncertainty principle, in a nutshell. That world is totally different from the world of every day. Nevertheless, we can understand it. But of course, we have to think about it in different ways from the ways in which we think about the everyday world. Our powers to penetrate into the depth of understanding the universe, both on the smaller scale, in the sort of physics I worked in, or the larger scale, in terms of the great spaces of space-time in the history of the universe, far exceeds anything that is necessary for everyday survival. And in fact, the mystery is deeper than that. For it turns out that the key to unlocking the secrets of the universe lies in mathematics, that most abstract of subjects. The greatest theoretical physicist I've known personally, I think, was Paul Dirac, who was a professor here at Cambridge, and of course was one of the big founding figures of quantum theory. He was once asked what was his fundamental belief. And he was a man of few words, so he strode to the blackboard and wrote on the blackboard, "The laws of physics are expressed in beautiful equations." And that really was his absolute conviction, and it lay behind his extraordinarily fruitful career as a theoretical physicist. Now, some of you will know about mathematical beauty. It's possible not all of you will. It's a slightly arcane form of aesthetic pleasure. It involves things like economy and elegance, and something that the mathematicians call being deep, which means you take something that looks like a very simple starting point, and as you explore it, you find it has many, many, many consequences. A prime example of that is the Mandelbrot set. You all know about the Mandelbrot set. You've seen these psychedelic posters. This endlessly proliferating structure of worlds and dragons' claws made out of worlds and dragons' claws. The definition of the Mandelbrot set you can write down in about 3 lines. But it gives birth to Mandelbrot's astonishment, of course. It gives birth to this proliferating complexity and beauty of experience. Mathematical beauty is something that those of us who speak the language of mathematics are able to recognize and to agree about. Like all forms of beauty, it's harder to define than to recognize, but we are able to do that. And it just turned out, in the history of physics, the 300-year history of modern physics, that it's only theories endowed with unmistakable character of mathematical beauty which have that long-term fruitfulness of explanation, which persuades us that they are indeed describing the physical world, an aspect of the physical world around us. Again, I go back to my hero, Dirac. Dirac once said, "It is more important, beauty in your equations, than to have a fit experiment." Now, of course, he didn't mean by that at the end of the day, empirical adequacy was something you could dispense with. I mean, obviously no scientist could possibly believe that. What he meant was this: you have your new theory, you have a go at solving it, you find it doesn't seem to fit the facts the experimenters are producing. Of course, that's a setback, obviously. But it's not necessarily absolutely fatal. Almost certainly, you would have had to solve the theory in some sort of approximation. Maybe you've just made the wrong approximation. Or it's just conceivable, actually, that the experiments might be wrong. We've known that happened more than once, actually, in the history of physics. So at least there's some sort of residual hope. But in Dirac's view, if your equations are ugly, there is no hope. The whole experience of theoretical physics testifies against ugly equations being able to describe the basic, fundamental structure of the physical world. Now, when we use mathematics in this sort of way to unlock the secrets of the universe, something really extraordinary is happening, isn't it? You see, what's mathematics? Mathematics is abstract thought. Our mathematical friends sit in their studies, out of their minds they dream up the beautiful patterns of pure mathematics. If maths isn't your subject, just think of it as being a pattern-creating, pattern-analyzing subject. What I'm saying to you is that some of the most beautiful patterns that the mathematicians can think of are found actually to occur, to be instantiated in the structure of the world around us. In other words, the reason within the mathematical thoughts of our minds and the reason without the structure of the physical world fit together in this harmonious way. Now that's a very significant, it seems to me, and profound and indeed unexpected fact about the physical world. And I think it would be incredibly lazy just to shrug our shoulders and say, well, gee, that's a bit of luck, isn't it? You chaps happen to be good at mathematics. I'd like to understand why science is possible in the deep way that it is. Why mathematics is, as Strack's brother-in-law, a chap called Eugene Figner, who also want to know about price, said, why is mathematics so unreasonably effective? Why is this abstract subject the subject to unlock the secret of it? What links together the reason within and the reason without? Now, science won't give me an answer to that question. Scientists are very happy, rightly happy, to exploit the opportunities that it offers and to enjoy the experience of wonder at the beautiful structure of the world progressively revealed by our investigation. Doing research in physics is pretty hard work, I have to say. It has a fair measure of wearisome routine, as every worthwhile activity does. It has its moments of frustration, as the good ideas of yesterday prove to be less persuasive in the cold light of today. But we keep at it. We keep at it because we want to understand the world. We have this thirst to understand the world. And science helps us do that, but it won't satisfy, it won't quench that thirst for understanding. So why does the reason within, the reason without fit together in a sort of way? Why is science possible? Why is mathematics so reasonably effective? I would like to have an answer to that. And now that's a meta question. It rises out of our scientific experience, but it's not scientific in character. And those sort of deep questions like that won't have a knockdown answer. I'm going to tell you what I think is the most persuasive and intellectually satisfying answer that I know to the question. But if you don't agree with me, I shall be sorry, but I won't say that you're stupid not to follow my argument. And it just, in fact, understand the world as a divine creation that, for me, makes sense of this connection between the reason within and the reason without. I believe they fit together because the thoughts of our minds and the structure of the world have a common origin in the mind of the Creator. I've been describing to you a physical world which, as we investigated, it has been found to be shot through with signs of mind, with rational beauty, rational transparency, rational order. And I'm suggesting it is indeed the capital M mind of the Creator that is recognized in that sort of way. And in fact, when I talk to my non-believing science friends, I know to talk to physical science, and of course that's my sort of little bit of science. This question of the deep intelligibility of the world is the one that intrigues them and in some ways troubles them most. It is such a striking feature. You can't just shrug your shoulders and leave it. There is a sort of cosmic religiosity which is somehow natural to the physicists. Einstein, you know, who was not a believer in a personal God, in fact very emphatically not a believer in a personal God, also said that he felt, when he made his big discoveries, felt like a child in the presence of the elders. There's some sort of mind or intelligence behind this wonderful order. Biologists, of course, see a different picture of the world. I've mentioned this in passing. They see a much more ambiguous picture. They see a world of great fertility, of course, also one of predation and parasitism. The evolutionary process is amazingly fruitful, but it's also amazingly costly. That's a different question, an important one. And religious people have to take it absolutely seriously, but it's not the question I've been asked to address today. I want to move on now and say something about the character of the physical world as physics has discerned it, and how that might be of interest and significance for theology. You see, the gift of theology or religious understanding, gift of science, is not to answer science's questions for it, as I've already said, but to set Science is understanding a broader and deeper context of an understanding intelligibility. So I've just been trying to do, addressing the meta question of the deep intelligibility of the universe. And the gift that science has to give to theology, and one that the religious people, a gift that they should accept with considerable gratitude and humility, is to tell them what the actual world is like in its physical and biological structure. And I want to say a little bit about how the world seems to a physicist. If I'd been at the end of the 18th century addressing that question, I would almost certainly have been pushed in the direction of saying the world is really an enormous piece, a very clever mechanism. We live in a clockwork world. Newton didn't think that, but Newton's successors, seeing the success of Newton's equations, his deterministic equations, began to increasingly see the world as just a colossal piece of cosmic clockwork. So that, particularly, that was so in France. So you get people like de la Mettrie writing a book called Man the Machine. Now there was always something, I think, a bit suspicious about that point of view, but I think really, at the end of the day, we know that we're not just machines. I have a very strong impression that I'm actually conveying some sort of thought to you, and you're responding to what I'm trying to. I'm not just quacking away in some sort of automatic fashion. There is a real engagement of minds between us. I think we are more than machine. See, a man the machine not only destroys human free will, which I think is a pretty basic human experience. I know it's very contentious and philosophers can argue about it, but it also, I think, threatens human rationality. If we're computers made of meat, what validates the program running on the computer? So, but I've always, I think, something implausible about this purely mechanical picture of the universe. And that picture, of course, wasn't modified in the 19th century by the discovery of field theory from the fundamental insights of Faraday and Maxwell. The universe is no longer seen as just a lot of billiard balls buzzing around and bumping into each other. There are these spread out fields, but fields, very important. Theologians often don't get this right, I have to say. Very distinguished theologians don't get this right. A field in itself is no more spiritual than any other form of matter energy. The field equations of classical physics are as deterministic as are the equations of classical particle physics. So this mechanical picture wasn't relieved by the discovery, the very beautiful and deep discoveries of field theory in the 19th century. But the 20th century did see the death of a merely mechanical view of the world. That death came about by the discovery of intrinsic unpredictabilities present in nature. And of course the key word there is intrinsic. These are not unpredictabilities which can be removed by calculating a bit more exactly or measuring a bit more precisely. They are a property of nature itself. As you all know, that first came to light in the first quarter of the 20th century by the subatomic discovery of quantum theory. Quantum theory is unquestionably a statistical theory. If I have a radioactive nucleus, I cannot tell you whether it's going to decay in the next hour or not. I can tell you the probability of that with very great accuracy, but I can't tell you whether an individual nucleus is going to decay or not. That is intrinsically unpredictable in that sort of way. And then, of course, a second discovery, in some ways even more surprising in a way, came in about the middle of the 20th century with the discovery of chaos theory. It turned out that even the Newtonian world, on its own terms, was not quite as clearly deterministically predictable as people had thought. Actually, great French mathematician Poincaré had noticed this in the 19th century, but nobody took it quite seriously enough. But people realized that even in the Newtonian world, the world, if you like, of everyday physics, there are systems so exquisitely sensitive to the slightest influence of their environment, their future prediction, behavior, is intrinsically unpredictable. Given the name of chaos theory, not a very good name, because it turns out that though the they're unpredictable. They're not totally haphazard or disorderly either. It's sort of mixture of the two. And I'm sure you all know that there's a scientific joke way of describing this, like all good jokes, a serious joke, of course, which is that the Earth's weather system can be in a chaotic state, can be in a sensitive state. So it is, you can say that a butterfly stirring the air with its wings, the African jungle today, is responsible for all this rain that's been falling over Cambridge in the last few days. I can say to you that long-term weather forecasting in detail is never going to work. The Earth's weather systems are too exquisitely sensitive to be susceptible to that sort of prediction. So that's a very surprising and interesting thing. So whatever the world is, it's not merely mechanical. It's something more subtle than mechanism. Then the next question is it also something more supple than mechanism? Because you see, unpredictability might be, as the learned say, an epistemological property or an ontological property. It might be that everything is really determined, but we are unable to ascertain all the factors that bring about what actually is going to happen. There are hidden variables, if you like. There are influences that work in the world that actually affect what's going to happen. Each of those nuclei has some sort of little internal clock ticking away which tells it when to decay, but we can't read that clock. And so its unpredictability comes from ignorance rather than from a genuine openness. But that's not the only interpretation. The other interpretation is, as they say, ontological. There may be a genuine openness in physical process. And that of course, would mean that the physical world was indeed not only more subtle, but also more supple in its character. Now, which of those interpretations should we take? Should we take ignorance, or should we take causal openness? Interestingly enough, it turns out that that's a question that can't be settled by physics alone. And we can illustrate that by thinking about quantum theory. I already said that quantum theory is a statistical theory. We can only calculate the probabilities of things happening. But what's that due to? Well, the traditional interpretation of quantum theory, stemming from Niels Bohr and the Copenhagen interpretation and so on, is an interpretation of genuine causal openness, that there is genuine indeterminacy in quantum processes. And that is certainly consistent interpretation of quantum theory, and the one held, in fact, by most physicists. And it was therefore a bit of a surprise in the 1960s when a very clever, slightly wayward chap called David Bohm came along and used an alternative interpretation of quantum theory, which gave exactly the same experimental consequences, but was deterministic in its character. Everything was determined, but we were unable to discern all the causal factors that were at work. So, physically, in terms of experimental consequences, you can't choose between Bohr or Bohm, between ignorance or openness. The choice between the two has to be made for reasons that which are meta-scientific, which lie outside science. I sign up with the majority of physicists and take the Bohr interpretation, mainly because though Bohm's theory is extremely clever and interesting, many of us think it's a little bit too clever by half. It's over-ingenious, so to speak. It has an air of contrivance about it, while the Copenhagen interpretation has a greater air of naturalness about it. But that's a meta-scientific reason. So for me, and most people, Heisenberg's uncertainty principle, not know both where it is and where it's moving, is a principle of indeterminacy, and not just a principle of necessary, unavoidable ignorance. By taking that interpretation, it doesn't mean that the future is a random lottery. It simply means that there is scope for other causal principles to be at work in the world, beyond those described by the canonical scientific discussion, the exchange of energy between constituents. And that is a metaphysically attractive idea, because one can begin to think that here may lies a room for maneuver to explain our surely basic experience of human agency. I can decide to raise my arm. When I do so, there is, of course, a bits and pieces account of what's going on. I mean, currents flow in the nerve, muscles contract, that sort of thing. But I decide to raise my arm. It's an act of me as a whole person to do so. And I think that the ontological interpretation of unpredictability affords scope for the action of new causal principles. We would expect them, I think, to be of a different kind from the constituent energy exchange principles of canonical science. They would involve, I think, they'd be holistic principles, they would refer to the total behavior of what's going on, and they would be concerned more with patterns of behavior, something you might call information, rather than with energy. And in fact, there are signs that are of an incipient revolution in scientific thinking about the world. People are just beginning in science to be able to discuss systems which are complex in their character without having to reduce them to constituent collections of bits and pieces. They can discuss them holistically in that sense. The systems so discussed so far are only mildly complex. They're nothing like as complex as a single living cell, for example. But they are mildly complex. Some of them are computer-generated models, and some of them are physical systems, which we call dissipative systems. If you have a physical system which is far from equilibrium and interacting with the environment, exchanging energy and entropy with the environment, a system can quite spontaneously generate remarkable forms of order. A very simple example of that is a phenomenon called Baynard convection. If you have fluid contained between two horizontal plates, and heat is being put in at the bottom, creating a temperature difference, the bottom is hotter than the top. What happens depends upon how big the temperature difference is. If it's only very small, the heat will simply percolate through, it will simply be conducted through the liquid. And if there's a big enough temperature difference, you will get bulk transfer, you will get convection. Hot fluid will rise from the bottom up to the top, cool, and down again. That happens spontaneously and in beautiful patterns. It's spontaneously organized into hexagonal convection columns taking place. That's an example of what you might call active information, a pattern-forming process operating on the totality of what's going on. The computer models are interesting. Also, a man who's written a great deal about that is Stuart Kaufman. He wrote a book called At Home in the Universe, and if you're seriously interested in it, that's a good book to read, quite demanding, but worth reading. He describes a model there, which is it's a computer model, it's a logical model, and it's what's called a God, I've got them. It has a logical name. You know it, Roger.
Yes, I'm not thinking of it.
Yeah. Anybody help me out? Anyway, it's a logical one, but we won't describe it in logical terms. We'll describe it in a sort of hardware metaphor. Suppose you have a system. I don't know why I have this terrible blank about this thing of light bulbs. Okay, each of them can only be in one of two states, either on or off. And the system is going to operate under rules by which each bulb in the array has a correlate with two other bulbs elsewhere in the array. And what they are doing now will determine what this bulb is going to do at the next state. The system develops in steps, and there is this linkage between them. So it's a purely sort of mechanical process. You can set it up on a computer. And the rules of correlation are very simple. And you'd think, well, okay, start the system off in random illumination, some on, some off. Nothing very interesting is going to happen. It'll just sort of flash away as long as that is it. But that isn't true. Very soon, the system will settle down into an amazing degree of orderly behavior. It self-generates an orderly behavior. If there are 10,000 bulbs in the array, in principle, there are 2 to the 10,000, which is about 10 to the 3,000. That's about 1 with 3,000 zeros following it, quite a large number. Different states of illumination it could be in. But very soon that system will be running through just a very limited cycle of possible states, about 100 states of illumination. There is the spontaneous generation of an enormous degree of self-generated order in these systems. So what's going on? Well, actually nobody knows really. I mean, at the moment, this theory of complexity is really at a natural history stage. People study these particular examples. It might be a dissipated system, it might be a computer model. There must be, of course, underlying laws, holistic laws of natural behavior that underlie this, but they are not known to us at present. And I think that in physics, in the broader sense, in the 21st century, this is going to be the most potential areas for interesting discovery, an important discovery, but their discoveries haven't yet been made. So what do you make of that? Well, it depends. Again, you have this choice. I mean, you can say that these things are happening just automatically. You can say that they are signs of some new independent laws of nature working. See, the computerized systems are totally deterministic. Otherwise, they couldn't be run on a computer. So, though you would never guess from the computer program that the model is going to generate this sort of patterned behavior, nevertheless, it must come about simply by the effect of the interaction. That need not be so in physical systems, because physical systems can have this openness that we've already discussed in terms of unpredictability, other causal factors being at work. I think this is just a glimmer, and it's no more than a glimmer, obviously, just a glimmer of science being able to move in a direction, be able to describe a physical world in which we could begin to consider ourselves as being inhabitants, to recognize ourselves as being inhabitants. Sadly, we do have very directing and basic experience of act as holistic agents in that sort of way. So, very interesting things are happening. And what we certainly can conclude from this, the arguments being made and the discoveries still to be made, that science has certainly, physics has certainly not established causal closure of the world on its own reductionist terms. That's a very important conclusion, I think, to read. I can take absolutely seriously, as I wish to do, all that physics can tell me about the processes of the world without believing myself to be some extraordinary complex automaton. That's, I think, a very worthwhile and important conclusion. Well, another aspect of the physical world, and that is strange and surprising, beyond our powers to anticipate. But of course, the paradigm example of that is quantum physics. At the end of the 1920s, after the great initial discoveries of quantum theory being made in the middle of the decade, the biologist J.B.S. Haldane said that the discoveries of his physicist colleagues, that they had found not only that the world was queerer than we thought, but clearer than we could have thought. The world is totally surprising. Only the nudge of nature pushing us in a particular direction will lead us to those sort of discoveries. In other words, our human powers of understanding, of a priori understanding, are distinctly limited. You see, quantum theory is, you all know, of course, that quantum theory, amongst other things, implies wave-particle duality, that light sometimes behaves like a wave, sometimes like a particle. And that essentially began to be discovered by Max Planck in 1900, and it took about 25 years to figure out what was going on. But any philosophy first-year student in 1899 could have proved the impossibility of something behaving something like a wave, flapping, something like a particle, a little bullet. Nevertheless, that's how nature does behave. A possibility that would never have crossed anybody's mind without the nudge of nature. And we have come to understand how that happens. It happens because in quantum theory we have what's called the superposition principle. In the everyday world, if I have a billiard ball, it's either here or it's there. Just two possibilities. In the quantum world, if I have a photon or electron, it could be either here, or it could be there, or it could be a combination, being partly here and partly there. A superposition, as we say, that corresponds to a well-defined mathematical way of formulating this possibility. So, and it turns out, I won't try to spell it out, I'll throw them out now here, but it turns out that that is a strangeness of the superposition principle, adding together things that common sense would say could never be mixed together, is what enables light to do the trick, make something like a wave, something like a particle. You see, the logic of the everyday world, which is essentially the logic formulated by Aristotle, is based on the principle of the excluded middle. Either A or not A. Either here or somewhere else. In the quantum world, there is a lot of middle between A and not A. There is a superposition of a bit of A, a bit of not A, a bit of here, a bit of there. So a quite different form of logic holds in the quantum world. The discovery of quantum theory hasn't just revised our thinking about the physical worlds, so to speak, but it also revised our thinking about what are logically consistent systems. A different logic holds in the quantum world, in the world of every day. And that means that the very important general lessons to be drawn from this. I want to now draw one or two lessons from this. I've talked about science as a search for truth and wider, deeper other forms of search for truth, and they have their experiences can help each other. The first lesson is that there is no universal epistemology. There's no single way by which you can know everything. You have to know entities in ways that accord with their own intrinsic nature. If you try and know the quantum world, when you turn in clarity, you'll just fail to do so. The quantum world can only be known in terms of its Heisenbergian uncertainty. So, I see friends shaking their heads, but that's what I'll know my colors that particular last. So I believe that there is no universal epistemology, but how we know things accord with how they know. So, for example, we know each other in one sort of way, but God will be known in a different way, the way in which we know Him. And secondly, there is no universal rationality. I've just told you that there is a quantum logic and an everyday Aristotelian logic. So the rationality, again, has to conform the nature of what we're thinking about. I mean, you can define fundamental rationality as conforming our thought to the nature of what we're trying to think about, but that form of that thought will be determined by the nature. And that means, I think, that the approach of physics, and also my approach in many other areas, is what I like to call bottom-up thinking. I don't despise top-down thinking. Top-down thinking is the idea there are certain general principles which you can start, from which you then establish clear and certain ideas, which you then discern to the consideration of particulars. The trouble is these clear and certain ideas have so often turned out to be neither clear or certain. I don't say there's no room for a priori top-down thinking, but I think that it is of a limited validity. We need also bottom-up thinking. By bottom-up thinking, I mean thinking that tries to move from experience to understanding, for our encounter with what we're trying to think about, with the way that we think about it. And I'm very happy to approach my theological convictions and religious beliefs in that sort of spirit too. And I've quite often written trying to set that out. So these are, I think, important. And again, there's a sort of cousinly relationship between science and religion, and they can learn from each other in the way the way they seek to find understanding. Second thing I want to say as a general lesson is a question of what is the ground for belief in reality. The quantum world is so strange that quite a number of people have suggested that though quantum mechanical ways of speaking are, of course, functionally very effective and enable us to make wonderfully, marvelously exact predictions, they are just manners of speaking. Quarks and electrons and photons and things are useful notions to enable you to predict more directly accessible phenomena, but they're not to be taken as actual descriptions of entities in the world. Well, I think that's not, I don't know. Scientists are instinctively realists. We believe that what we know is a guide to what is the case. And I believe that there really are electrons and photons, and indeed there really are quarks. Quarks, 25 years I worked in physics, was essentially the years of the discovery of the standard model, the quark theory of the structure of matter. And at the end, there was a lot of struggle on the way, and lots of problems, but in the end the dust settled, and then we all now believe that matter is made of quarks. But nobody had ever seen an individual quark. We believe that they're so tightly bound within the protons and neutrons that they constitute that no impact is strong enough to knock them out. It's always consoling to have a word for something, and so we say quarks are confined in a sort of way. So you see, quarks are unseen realities. They're unseen, for sure, but we believe they're also realities. And the reason we believe they're realities is that that belief makes sense, deep sense, of great swathes of more directly accessible behavior, properties of protons and neutrons, and so on. So scientists, every physicist, perfectly happy to believe in unseen reality, provided that those realities have extrinsic power in relation to more directly accessible forms of experience. And again, that's a message I think one can transfer from physics to theology. I believe in the unseen reality of God, because that belief makes sense of great swathes of spiritual experience and understanding of the world. So this is, again, a cousinly relationship shows up. The third cousinly relationship goes back to this question of the surprising character of the physical world and its unexpected character. That means, what I've been saying so far, I'm actually saying this, that the natural question for a scientist to ask, both within science and also beyond it, about some proposition that's being made, is not, is it reasonable? It's if we felt we knew beforehand the shape the reason has to take. Nobody, I say in 1899, nobody regarded wave particle duality as being reasonable. It's absurd, oxymoronic. So the natural question for scientists to ask is not, is it reasonable, as if we felt we had prior knowledge of the shape the rationality had to take, but a question that is both more open and more demanding. And here's something like this: what makes you think that might be the case? You see, it doesn't seek to label down beforehand the shape that an acceptable answer has to take. It's open to surprise. But if you're going to make some surprising assertion to me, you'll have to produce motivating evidence for that belief. If you're going to talk about wave-particle duality, you'll have to talk about interference effects which show wave properties, photoelectric effect and things like that which show particle-like properties. Motivated belief, open motivated belief, is the natural quest for scientists within science and beyond it. Again, I'm very happy to approach my religious beliefs in a similar sort of way. There are some lessons, some cousinly lessons between them. A couple more points I want to make, then I'm finished. Another aspect of the physical world that science has discovered, which is very striking and in some ways unexpected, is how deeply relational the physical world has proved to be. That old picture of individual atoms bumping around in the void really, again, has passed out of our physical understanding of the world. And that's manifested in various ways. For example, Einstein's theory of general relativity ties together space, time, and matter in an intimate relationship. So that matter curves space-time, and the curvature of space-time curves the particles of matter. It's a sort of package deal. You have to have the three together. The most striking of all is a phenomenon called quantum entanglement. And that is this. Once two quantum entities have interacted with each other, like say two photons, they remain in some sense a single system, able instantaneously to influence each other, however far they may subsequently separate. So if one of those photons stays here, the other one goes, as we conventionally say, beyond the moon. If I do something to the photon here, you have an immediate effect on the photon behind the moon, an immediate causal effect on the photon behind the moon. Quantum entanglement. Curious enough, even the subatomic world cannot be described atomistically in that sort of way. It's interesting, it was Einstein, you know, being one of the grandfathers of quantum theory, his explanation of the photoelectric effect, came to hate his grandchild because he wanted the world to be absolutely unproblematically objective. He was deeply convinced of the reality of the physical world, but he mistook reality with objectivity, and he hated the unpredictability and cloudy fitfulness of quantum theory. He was always trying to kill off his grandchild. And in the middle 1930s, with two young colleagues, he felt he succeeded in doing that because he discovered that quantum theory had this implication, which nobody had noticed before, that of this togetherness and separation, this mutual influence of quantum entanglement. He thought that was so spooky, as it were, so spooky, we must show there's something wrong with quantum theory. Years after his death, very clever experiments in Paris showed that this is indeed a property of nature. The world is not a collection of atoms. It is something much more relational in that respect, and that is very interesting and I think significant fact about the world. The final thing I want to talk about is this, which is a challenge that physics, I think, does produce for theology. Because every story that physics tells, in the end, ends in chaos and decay. We are going to die on a time scale of tens of years. The universe itself is going to die on a time scale of many billions of years, most probably by continuing to expand, becoming more and more cold, more and more dilute, till all life anywhere must disappear from it. Everything ends in futility, according to physics, the unfolding of present process. Another way of looking at it is to say that the second law of thermodynamics lies behind this tendency to decay. The second law of thermodynamics says that if you have a system which you don't interfere with from the outside, it will become progressively more disorderly. Entropy, the measure of disorder, will inevitably increase with time. Just think about your desk. You never tied it up. You see the point of it. And the second law of thermodynamics is essentially a statistical law. Because there are many, many, many more ways of being disorderly than there are of being orderly. So the waters of chaos continue to rise. In the end, all ends in chaos and futility. And these are things that we should take seriously. Of course, the response of theology is that the science's story, though it's a true story, is not the only story to tell. There is a vertical story, if you like, of the faithfulness of the Creator, for whom death and chaos and decay is not the last word. The last word lies with God. It is the faithfulness. The only ground we have of believing in a destiny beyond death, for ourselves or any other part of creative reality, lies in the faithfulness of God. There is no natural expectation of that kind that science itself could describe. But if we believe in a faithful God, indeed I do, then of course there is every expectation that the old creation will eventually be replaced by a new creation. And as a Christian, I believe that's already going to happen, the resurrection of Christ. But there we are. We've had a sort of book's tour around a number of issues of physics. Let me just go back to where I started in the way. Say that I like very often to talk of myself being two-eyed. I look at the world through the eye of science, through the world through the eye of theology. And I believe with that binocular vision, I can see further and deeper than I could with either eye on its own. That's what I think. Now you've got a chance to tell me what you think. Thank you very much.
Thank you, John. Well, we've got a good length of time for questions, so over to you. Yes?
Do you think there's...
Can I ask you to
Yes.
stand up if you ask me a
Oh,
question?
of course.
Actually. Also to be speak
loud.
as loudly as possible.
I'll try. Okay. So do you think this quantum world logic could explain pluralism of religions?
I don't think so. That seems to me no, I don't think so. I mean, science can be a powerful source of metaphor, and sometimes scientific metaphors are helpful, transferred to other realms of discourse and search for truth. But the problem, the most difficult problem for religious belief is surely the problem of evil and suffering. I don't need to explain that. I'm sure they will crop up more than once. Of course, it is some school. The second most puzzling problem, at least for a scientist, is the multiplicity of the world religion. You see, it contrasts with the way, I mean, science started, if you like, in 17th century Western Europe. Now it's universal. You stop somebody in the street in London, or in Delhi, or in Tokyo, and you ask them what matter is made of, and you choose the right person, they'll say quarks and gluons and electrons. You stop three people in those three cities, ask them what is the nature of ultimate reality, and you're likely to get three very different answers. Of course, the world faith traditions are, in one sense, all talking about the same area of human encounter. Some we might call it encounter with the sacred, but you have such different things to say about it. They're not all saying the same thing in culturally different languages. I mean, is the human person something of abiding and continuing significance, as the Abrahamic faiths all say? Is it something that is recycled through reincarnation? Is it something that is ultimately an illusion, which the Sikh believes? Those aren't three sets of people saying the same thing, different cultural languages, they're clashes. And it's very strange that that's so. And I think that a facile solution says we know everything, all the others are wrong, isn't right either. People of other faiths, this is never true of Jews, but people of other faiths are not strange people in faraway countries that believe all the things. They're living down the street. You see the spiritual integrity of their lives. It can't be just dismissed like that. So I think that a very big problem, not just for the 21st century, but I think for the third millennium, is to seek to have a dialogue between the world's faith traditions.
Thank you. Yes.
I'm not entirely sure you will want to answer this, but I'd like to ask
I'll try.
Wouldn't you consider that within the problem with the human mind, it's essentially dualistic? And you've got the problem then Jesus coming along saying, I and my Father are one. That is to say, you've got Jesus saying there's only one way of looking at things. That's the divine way. And the human mind says, well, no, I want to look at it different ways. Is there any way, is it something you've ever considered? Because to me that seems to be the huge stumbling block that we have, is that we try to interpret things from a human point of view when the human point of view is essentially corrupt.
Well, I've confessed already, I'm very much a realist. I believe there is one world and one truth. And I believe that partly because I believe there is one God who is the creator of that world and the guarantor of that truth. Now, we only have very partial insights into that, obviously. That's part of the problem of the world faith tradition in relation to that. And of course, we are often mistaken, and often motivations, both conscious and unconscious, cause us to make errors in that sort of way. We have to be careful, I think. Nevertheless, I mean, I do think, both within science and beyond it, that we are able to find enough truth to commit ourselves to it without being certain about it. I mean, there's a longing, it seems to me, to have certain indubitable truth. I think that's just a mistake. I don't think it's available in science itself. I mean, there are all those clever chaps like Kelvin at the end of the 19th century thought they got, you know, one about the physical world. there is a richness and a mystery in the world in which we live, which we have to be open to. And that doesn't mean that doesn't mean it shouldn't. We have to steer. I'm an alien, remember. We have to steer a course, a middle course between two extremes. One is thinking we can never know anything. The other is that we know everything.
Dr. Polkinghorne, I have a question about the apophatic dimension.
Yes.
The early Christian theologians
Yeah.
placed a heavy emphasis on the apophatic dimension. However, how much you try, you never comprehend the reality of God. Does science, in its quest to understand everything, acknowledge this apophatic dimension in any way?
Well, I think a science that's true to itself, as I say, doesn't claim for true absolute knowledge in that sense. But obviously there is the apophatic dimension in Christian thinking, which you testify, particularly you're like Gregory of Nyssa and some of the early fathers of the church, which says that there is a mystery in God, which God will never be caught in our rational nets, and that surely is obviously true. The finite can never totally understand the infinite. So we have to be realistically modest about it. On the other hand, of course, in science, we do transcend the physical world. And one of the reasons why science is so successful is we are able to interrogate it, not exhaustively. I mean, you never know what's going to go around the next scientific corner. I mean, who knows? I mean, it's nice that the LHC seems to have discovered the Higgs boson, but it would be even more interesting to discover things we hadn't thought of beforehand. So there is a sort of richness, even at the level of the physical world. But of course, when we talk about the infinite reality of God, then we have to be circumspect and realistic. But again, I think the answer is neither intellectual despair nor intellectual hubris. So the apophatic dimension of theological thinking is an important dimension, but it's not the only dimension, it seems to me.
Thank you. Yes?
How would one reconcile the notion of a constant God and a created universe that is intrinsically, or as you call it, ontologically chaotic and subject to decay? A simple example is that Jesus, as the Son of God, or part of the Trinitarian God, died on the cross.
Right.
So hasn't God been changed by the experience of death itself?
Well, that's a very deep question and a good one to address. I mean, I think myself that when God brought into the world a evolving temporal creation, I think that was God's purpose, not to act as a continuous creator, not simply to snap the divine fingers, bring it into being, simply keep it in being from distance, but to have an unfolding process by which God's purposes are realized through the process, the divinely ordained process of creation. And of course that involved, if you like, a risk on God's part. I mean, it involved eventually coming to be of free beings, or relatively free beings like ourselves. And so God accepted that, and I think that a very important idea, I'm stuttering a bit, but a very important idea in contemporary theology is that the act of creation was a divine act of kenosis, a divine limitation. You see, Christian theology has to steer between two pictures of God's relationship to creation. One is the detached, indifferent, deistic spectator, who can't be the God of love. But neither, of course, can the cosmic tyrant, whose creation is no more than a divine puppet theatre. So there has to be a steering between the two. And God allows creatures to be themselves, to make themselves, takes that risk. I believe that God is in that sense vulnerable, and I believe that in fact the incarnation, I mean, it exemplifies God's willingness to identify with that process to the uttermost. That's one thought that comes to my mind. The theological necessity to have a balance between grace and free will, if you like. That would be another way of putting it. It's also very interesting that there's an insight of physics, which is that regimes in which really new things happen are always regimes which we like to call at the edge of chaos. Regimes where a degree of order and a degree of disorder, of regularity and of openness, interlace each other. If things are too orderly, they are too rigid for anything genuinely new to happen. You can get rearrangements, you don't get anything really new happening. Of course, if they're too disorderly, anything that they're too haphazard, if anything that new came into existence, it would just pass away. To get fruitfulness, you need a very delicate balance between order and disorder, chance and necessity, if you like. If there was no genetic mutation, there would be no new forms of life. If there was genetic mutation all the time, no species would be established on which natural selection could act in a sifting and preserving way. That's how some people do what you're asking, I think. Anyway, thank you.
Thank you for that, yes. So you'd be somewhat revisionist in terms of sort of classical doctrines of immutability and so on.
No, absolutely, yes. I think that's right. I mean, there's some significant. There's a significant movement in contemporary theological thinking which does revive the sort of classical theology. That's right. So omnipotence is not equated with total control.
Right.
Steadfastness is not equated with immutability in some sort of rather more trivialized sense, so I say. I think that God accepts risk in that sort of way. Of course, that's very contentious, but that's what I think.
Well, thank you, John. Yeah, more questions? Yes.
Or comments. I mean, I'm not
comments. Yes. Or comments.
I'm here to tell me all the answers.
Well, first of all, thank you for your talk very much. And I want to know, what do you think about the multiverse hypothesis? Very, very quickly.
Well, that's really Paul's job to do with anything talking anthropic principle. The multiverse, our universe, we do seem to live in a very particular, very special universe, as Paul will be explaining after coffee. And in fact, carbon-based life couldn't come into existence unless the world had all sorts of fine-tuning in its given physical fabric. That raises then the question of what do we make of that? Is it just a bit of luck again? That would be rather lazy, I think, to go that way. Is it a sign of a creator's purpose? Which is a sign that there's just a vast array of different universes, all with different laws of nature and so on, and we just happen to be the winning ticket in this cosmic lottery, so to speak, that self-conscious beings like you and me have been able to emerge in its history. And the multiverse became very popular by scientists who were struck by the particularity of our universe, but didn't want to, a sort of threat of theism, didn't want to see it in those sort of terms. But of course, it's a metaphysical assumption as the existence of a creator. We have no direct access to these other universes. They're unobservable by us. There are speculative theories that might suggest their existence, but they are highly speculative theories. So it seems to me, I think poor William Ockham is turning in his grave. It seems an extraordinary prodigal ontological assumption. There are these trillions, and there really have to be a lot of them. And it isn't even necessary, without some further consideration, it solves the problem. It's just having an infinite, even an infinite number of things doesn't mean you get every desirable property. For an infinite number of even integers, none of them has the property of being odd. So, you know. But anyway, I prefer this to my colleague later on.
Yes, and we'll have more, no doubt. Jennifer at the back has a question.
Could you say a little bit more about your views of the long-term future of the universe? You said that from the natural physical perspective, the universe is going to expand and cool and everything will die, and it's a bleak future looking only through the eyes of physics, basically. But through a theological perspective, there is hope. And so I wondered how you saw theologically this coming of the new heavens and the new earth. Do you see that as a very sudden transformation of the universe, or would it work itself out through laws of physics in ways that we don't yet predict? Or how do you theologically see this transformation into the new heavens and new earth that does give hope, when the natural physical picture of the future is one of basically death?
That's good question. I mean, I do I don't see it as being likely at all, in the slightest degree likely, really, to be a happy outworking of unknown laws of physics at the moment. I think that it does require a real transformation. Then theologically, that raises the question, if it must be something more than just an apocalyptic, clear, wiping the slate, God having a second go, trying to do rather better the second time than God did the first time, and that can't be right either. And I think that, I've written a certain amount about this, I think that God's creative purposes are intrinsically two-step. God first of all brings into being a universe which can exist at some distance from the infinite reality of the Creator, so that creatures are able to be themselves and to make themselves. The finite beings would just be overwhelmed by the naked presence of the infinite reality of God. But God's eventual purposes is to draw creatures, or those who are willing anyway, into a more intimate relationship with the divine life. And that intimate relationship will transform the nature of the world altogether. We live in a world that contains sacraments, covenanted occasions, which the veil between us and God is to some extent thin. The world to come will be totally suffused with the divine presence, will be totally sacramental in that sense, I believe. And I think that's how, so God is transforming this world, and I believe that transformation has begun from the seed effect of Christ's resurrection. The tomb was empty because the Lord's risen body is the transmitted, glorified form of his dead body. So that's I mean, that in outline is how I think about it. I mean, as I say, I don't want to have a just, okay, that's it, I'll try again. But so the present creation has value and importance. It's the raw material which the new creation is going to be made. And I think that makes sense.
Yeah, thank you.
What can you tell about last book of Stephen Hawking's, The Grand Design, and its ultimate explanation? Gravitation is the ultimate explanation of everything.
Well, I'm ashamed to admit I haven't read that book actually. But I think I read a lot about it, which is a poor substitute, I agree. But what I have read suggests that it is Steve again making this mistake about I mean, if M theory or whatever it is really explains everything, M theory is itself not self-explanatory. It doesn't come for free, not at all. M theory is not nothing. It's a very considerably complex and elaborate something, and you can't get away from the question of why is there something rather than nothing. So as I say, I mean, I enormous respect for Steve, both as a scientist and also, of course, as a person. An extraordinary life he's lived and now becoming his terrible handicap. But he really is pretty, I think, pretty naive about other philosophical and theological questions.
Gravity is negative energy and matter is positive energy. They cancel out, therefore the universe can create itself out of nothing.
Well, yeah, I mean, people have known negative and positive energy. Yes. That's been around for a long time. But again, I mean, if you just have nothing, it doesn't instantly separate into plus and minus. I mean, it's a very naive mistake in my opinion.
Well, I agree with John about that. But anyway, yeah. Pat, did you have a question, Pat?
It's really here.
Oh, sorry, lady here.
Can I ask a question? You know, when you are talking about everything ends in chaos and decay, it sounds very, very negative. But if you see decay as being set free again, you know, from order has also something. You can say negative because it bounds everything, it binds things, and if it's disorder, it's chaos, it's set free again. When you have built a very, very simple example, if you have building blocks in a kindergarten, and you create something beautiful with it, the joy children have to destroy it, and there is a true joy in it to see it set free again. And then they start again. So I was just wondering, is the new universe just to fix everything again, because decay has such a negative impact, and is that necessary to have such a negative impact. I think there are other religions around who might see differently than the Abrahamic religion.
Well, I'm sure there are, and I think it would be very interesting to explore that and to hear from people of those traditions. Well, I mean, I think it's a little bit of a optimistic abuse of language to describe decay as freedom. I mean, by itself, decay, it seems to me, is just decay. I mean, as far as the scientific story is concerned, the universe will eventually end up as just extraordinarily cold, structureless collection of radiation. And that has then reached thermal equilibrium and has no prospect of change in direction at all. So, I mean, I think of course, I mean, there's a very, and it's a very repeated sense in Christian thinking that death and resurrection are complementary necessities. But that's only possible because we believe there is a divine agent who is the resurrector.
Yeah. Yes.
Thank you for the presentation. It's just a comment and a question.
Yeah.
As a comment, I think it's very interesting what you said about mutations and life being at the edge of, you need to have some degree of mutation and some sort of degree of fidelity in the replication. I think biologists are working around this idea, and I think it's a good example. They are working around the idea of quasi-species. Some viruses are mutating so much that they are losing the stability, but at the same time they need some small level of fidelity. So in some families of viruses they talk about quasi-species. There is not a real species because they are just living at the edge of chaos. They're losing the stability and the. I think probably it's a good illustration of that, more than simply in animals. And the other thing I want to ask is about this idea of having kind of two different levels of rules, or like the rules for quantum world, and then our more traditional rules for the big object. How does it work with a situation that is in the middle, the situation of chemistry, where you have molecules that have to live in between both worlds? What is the approach? Because I don't think we can really live with two completely separate logics. There's going to be a level of reality where both have to merge in some way. I don't know exactly how it is.
That's an extremely good question. I should have really referred to it in my talk. I mean, there are many unsolved problems in physics itself. Physics very often gives you a very good understanding of what's happening in a particular regime. But there are many puzzles about how one regime relates to another regime. And the biggest unsolved problem in quantum theory is to understand how this cloudy and fitful subatomic world gives rise to the particular and an orderly world, our everyday experience. A particular example of that is called the measurement problem. You measure, if you have a, say, an electron, it could be either here or there, you make a measurement, this time you find it's here. What made it be here this time, rather than there? You can calculate the probabilities, but what actually brought about that definite result, definite occasion? It's an embarrassment for physicists to say that 85 years or whatever it is after the discovery of quantum theory, we don't know still the answer to that question. We don't know how different regimes relate to each other. Even physics understanding of the physical world, its own terms, is patchy. Another example is quantum chaos. You have a chaotic system. This is extreme sensitivity. It soon begins to appear to depend upon tiny effects below the level of Heisenberg uncertainty. Okay, you say, let's put quantum theory and chaos theory together, have quantum chaology, as people say, and we've got a wonderful synthesis. You can't do it, or at least we can't do it. The reason is that the two theories are incompatible with each other. Quantum theory has a scale. There's a meaning to large or small in quantum theory. It's the scale set by Planck's constant. Chaos theory, as you all know, is fractal in its character. And fractals have no scale. They're the same or never scale over them. You can't put together a scale-free theory and a theory of scale in a consistent way. So we can't even do that. So yeah, thank you very much indeed. I really should have said that. Yeah,
Does this notion of decoherence help somewhat with the
well, no, but it simply, yes and no is the answer to that. What decoherence does essentially is to explain why you don't see on a macroscopic level the interference effects that you would see on a microscopic level. But it doesn't explain why you get a particular. I do a little bit of physics geography. We think in terms of the density matrix. Means the density matrix becomes diagonalized through the effect of interaction with this background radiation field. But it doesn't say why on a particular case I get this entry on the diagonal rather than another one. So it's an important step, but again it shows an interesting connection between environmental effects and individual effects, but it doesn't solve the problem.
Thank you. We've got maybe just a couple of minutes for, yes?
As a Christian and as a physicist, what is your view of the soul as opposed to the body?
We'll have more about it during the week, but it'd be great to get John's comment and solution to the mind-body problem in 2 minutes, John.
Well, that's right. Well, let me say, I can do no more than wave my hands and what I do is in the right direction. I certainly don't take a dualist view. And the difference definitely of that has always been to understand how this substance mind interacts with that substance matter, and that hasn't been solved. So I want to take what people would tend to call a dual aspect monism view of things, to say that there's one structure out of which the world is made, created world is made, but we encounter that in different aspects, a mental aspect, the material aspect, and somehow or other there's complementary. Just as I'm going to use an illegal analogy, but just as waves and particles fit together for single entity of light, so maybe mind and matter, in that sense, fit together. It's an aspiration rather than anything else. And I think that's the direction we try. And all this merging science and complexity theory with this sort of hopeful dualism, intrinsic dualism between energy, information, might be a little bit of a sign in that direction as well. But all this is one of the physicists I knew was Wolfgang Pauli, who had a very acerbic tongue, a great pioneer of quantum physics. He used to wag his finger at people and say, "No credits for the future. Don't tell me that your theory is going to work out." No, you have to make it work now. I don't want to claim credits for the future, but that's the best I can do.
Well, thank you, John. I think we have to draw things to a close there because coffee has arrived. And there will be a box, as I say, going on the piano for your written questions for the panel this evening. And John has kindly said he can come back for the panel, which is great. And so let's give John a great round of applause for getting